So in this video, I'd like to go over some of the sigmatropic rearrangements and throw a couple of problems on the board, similar in fashion to the way that I did the electrocyclic uh, portion of the pericyclic category. I'm going to throw a bunch of problems up on the board. I'll talk about them for a little bit, and I'll have timestamps if you're just interested in the question and the answers to follow. So without stalling too much more, let's go ahead and get into the first one. Okay, so here's the first one. Go ahead and try to figure out what the product would be. And if you could figure out a name for what this particular sigmatropic rearrangement is called, go ahead and name it. So first, I'm going to start these problems by drawing my arrows, so my mechanism. So I think that helps kind of explain what's going on. And in this particular problem, it's thermal, so I'm going to look for 3 electrons to push around, so an odd number. So I can see I can do something like this. And opening up the ring just in this way that I've drawn right now, the double bond there, and our methyl group is still right here. And if you decide to name this molecule or this reaction, it'd be called a cope rearrangement. So cope rearrangements refer to 1,5 sigmatropic rearrangements that have regiochemistry retained. So I haven't really moved around any atoms. I just kind of picked one bond and made it into a double bond and let some electrons be pushed around. I do believe cope rearrangements are usually done under thermal conditions. I don't think I've ever seen them done with photochemical, but you can look out for that just in case. So let's go on to the second problem I have. So for this one, kind of sneak peek, it's going to involve more than just pericyclic type chemistry. So we're going to have to recall to some of our old chemistry from previous chapters in organic. But first, I'm recognizing that I have a 1,5 system right here. So the only place where I can label 1,5 would be 1, 2, 3, 4, and here's the 5th double bond going that way. You can go ahead and check for yourself, but if I decide to go the other way, so instead, if I decide to go that way, I actually won't have a 1,5 system, and so it at least wouldn't fall into the category of something that is cope-like. So that kind of gives away what we're going to do here. But since we now know it's going to be something cope-like, let's go ahead and push electrons around so that we can see what's going on. That single bond break and form a double bond down there. And when we do that, we're going to have to push these electrons like this. So what does that give us? Well, we've now have an enol, which is going to come into play in a second, and our second double bond right here. So under thermal conditions, and really actually under pretty mild conditions, tautomerization happens quite readily. And so that's what I was referring to earlier about recalling some older organic chemistry. So remembering that enols are actually less stable than ketos the majority of the time. There are some exceptions. Tautomerizing here to its most stable, lowest energy state is going to be favorable. So, excuse me, but if we did that, we'd be left with this. And so I'm going to draw it a little bit neater just so we can clearly see what's going on. And I believe this looks like 9 carbons. So I'll just count real quick. 1, 2, 3, 4, 5, 6, 7, 8, and there's the 9th at the end. So I have a 9 carbon chain. A 9 carbon chain with double bonds at the end, and at the 4th carbon, there's going to be our ketone. So just like that. And this might be a nicer way to write what the final answer looks like. Okay, so here's another problem. Go ahead and try to solve this one real quick. And I guess actually I should mention If anybody was curious, the name of the last reaction, I mentioned cope a few times, but it actually, more specifically, you'd call it the oxycope. So the oxycope rearrangement. And so that was for the previous problem. But for into this problem, go ahead and try to solve it real quick. If you can, do the mechanism. It's always helpful, and we'll talk about it in a second. So I'm going to start with the mechanism. Thermally, so that tells me, again, I should be looking for something with an odd number of electrons, pair of electrons moving around. I think the most obvious thing is probably going to be to break this, this ether type bond. So if you break the ether, you have to do that. You have to push electrons that way. And then to avoid 5 bonds to carbon, we'll end up letting electrons go through that carbon and attaching to this end of the cyclopentate. Product-wise, we will end up with this right here. So we have the methyl group that didn't move. Looks like now we have a ketone right here, and then a cyclopentane, and at some part, I could do it right here, or I also could have done it right here. It doesn't matter. We have that ethane group. So that's what we should have, at least for the beginning product. So again, we have a situation where tautomerization is going to happen because recognizing that this group right here is referred to as an enone. So this is an enone. And enones tautomerize into enols. And again, usually the keto form is more stable than the alcohol form. But in this case, when we create the alcohol, we're actually creating a phenol. So phenol implies a benzene ring. And since benzene rings are lower energy, more stable, that's going to be more favored. So I'm going to draw an arrow. Let's do it like this. An arrow, and I'm going to write tot for tautomerization, just abbreviating it. And that'll get us to this product. And we said enol, methyl group didn't move, and lastly, this pentane ring. And just like that, and that'd be our final product. Okay, so on this problem, it's a little bit different. I'm actually asking if we could figure out what conditions, so either photochemical or thermal, will get our reactants to our products. So in this case, our products look like it's more stable because we have that benzene ring. So how can we do that? And go ahead and include a mechanism too. So starting with the mechanism, I'm just going to move electrons around in the way I think that they are going to fit our product. And so the first thing I think to do would be to move those electrons there. When we do that, we're going to have to move these electrons down, and to avoid having 5 bonds to carbon, that hydrogen needs to move. So let it move and attach to the other end of that first double bond. And that would get us to the product, and so now we have to just figure out what conditions allow us to do this. And so remembering that thermal conditions generally implies an odd number of electrons in sigmatropic rearrangements, or odd number of pairs, I should say, of electrons in sigmatropic rearrangements. And photochemical rearrangements happen with an even number of pairs of electrons, generally, in sigmatropic rearrangements. And so recognizing that there are 3 arrows that I've shown on my mechanism, I should expect that the answer to this was made under thermal conditions. And so maybe I will do this in a dark blue color so we just get the point. It's all kind of crammed in here. And so I have another problem just like this, and let's go ahead and go to that one right now. Okay, so again, very similar to the last problem, how can we get our reactants to our products in this case? So I think the easiest thing, of course, would just be to draw the mechanism. And just like before, we need to move this hydrogen to avoid 5 bonds to carbon. So do something just like that. Now remembering from the last problem, thermal conditions, usually you're going to see an odd number of pairs of electrons moving around, and photochemical would be the opposite, so an even number. In this case, we have an even number of pairs of electrons moving around, so we should expect that we did this under photochemical conditions. So that's H nu. I've kind of made it messy, but H nu would be the answer here. Okay, so on this problem, I'm giving you the reactant. I'm telling you to do a 3,3 sigmatropic rearrangement, and I'm also telling you that it is done with heat, so some thermal conditions. So go ahead and try to figure out what the product would be, and then we can talk about it after. So mechanism-wise, we should at least recognize that 3,3 refers to 3 different groups, or I'm sorry, 2 different groups of 3 atoms. So I'm looking around and I think that there are 3 atoms. I can say 1, 2, 3. And if I stopped counting right there, and then I started at the oxygen, so the oxygen is 1, 2, and there's the 3rd position. Well, that would fulfill the 3,3 requirement that I've listed underneath the arrow right here. So you can kind of think that if you broke the bond right there, you'd have 3 atoms that are going to be part of your pi system and doing something in that pi system, floating around. And then on the other end of that kind of dashed line are the extra 3 atoms that are going to be helping the previous 3 reattach to the molecule itself. So with heat, we should expect that there are going to be an odd number of arrows moving around. So let's go ahead and start doing our mechanism. If we did that, we'd have to break that bond, move it to there, and then finally let that bond attach to the opposite end of this double bond. So we do have an odd number of arrows, so that means that we are in the correct orbital, so this is going to work fine with heat. Product-wise, we'd have this sort of thing going on here, and a double bond, and it's connecting like this. Let's make sure I have my bond correct. And that'd be, I guess, your intermediate product. You should remember that enones can tautomerize very easily into enols if the enol is part of a benzene ring. So in this case, if we did tautomerize, we'd be left with a phenol derivative, which is more stable and will allow us, or will actually be our product. So here is the phenol, and then just attach the part that we actually moved, and that'd be our product. Okay, so another similar problem, just like the one above. I'm telling you guys the reactant. I'm telling you guys to use thermal conditions and to do a 5-5 rearrangement. So go ahead and give this one a try. So counting where 5-5 is going to come from. I'm just going to go to wherever I think the pi system is going to start, or where p orbitals are going to start playing around. So this pink dot would be 1, 2, 3, 4, and there's the 5th. So I'm going to draw a dashed line like I did on the previous problem. And then I'm going to start counting from the oxygen. So there's 1, 2, 3, 4, and 5. And so our 5-5 rearrangement is going to take this stuff. So it's going to take this stuff and move it to this last pink dot. So how do we do that? Well, let's push electrons around. If we suggested something like this, we're going to get something very similar happening. And really, it's the same exact mechanism. It's just we've added 2 more arrows, which is good, because if we added 1 more arrow, then we'd have an issue because we'd have an even number of pairs of electrons moving around, and that would cause some issues with thermal conditions. So in this case, we have 5 arrows, which is an odd number, which is great. So we can confidently draw our product, or I should say our intermediate. That's not the best benzene ring. So our intermediate, and it's going to look just like this. So there's 1, 2, 3, 4, 5, 1, 2, 3, 4. There's the 5th. And at the end, there's a double bond, and there's also a double bond right there. So again, this is just an intermediate because it's an enone. We're going to let this tautomerize. So when you tautomerize it, you get back your aromatic ring. So there's the aromatic ring. And there is your 5-carbon chain that you moved from what was the top to the bottom. So let's go on to the next. Okay, so here is the third one that looks very similar. I'll have one more after this. It's also very similar. But again, given the reactants, thermal conditions, and it's a 3-3 rearrangement, figure out what the product is. So moving electrons around, I'm going to look for 1, 2, 3. So there's my 3, my first 3, and there's 1, 2, and 3. So that's how I'm going to do my 3-3 rearrangement. Let's move the electrons around, doing something like this. So we should be looking, are there an odd number of arrows? In this case, we have 3, which is odd, so we are good right there. And our product will look just like this. Make sure I have all the correct bonds. And that looks good. That should be what our final answer looks like. So our double bond is actually 1 carbon away from where we've attached, which is what we've shown right here. And we no longer have this kind of awkward branching. So this would be our, I don't know if I said final, but this should be our intermediate because again, we have the enone. So just tautomerize to get to our actual final answer, which gives us back that aromatic ring. Okay, so last one of this type, I promise. Thermal conditions with a 5-5 rearrangement, and you're given the reactant, figure out what the product is. So as characteristic with the other problems, kind of guess that this is where we're going to be breaking our our first 5 from our second 5. So let's now indicate which 5 those are. So there's 1, 2, 3, 4, and here's the 5th. The oxygen now is 1, 2, 3, 4, and the pair position is the 5. So now let's connect them, and I'm going to skip one step because we can already tell that since these are, or this one's just like the previous 3 problems, we'll end up with an enone, and we'll have to tautomerize that into the enol. So I'm right away going to skip that tautomerization because we know it's going to be an issue because we've done these problems 3 times now. It's getting repetitive, and we know that this is going to end up with an enol in the end. So now we just have to attach that final group. And I guess I should actually draw the mechanism so we know what's going on. And you're not surprised because this looks just like, I think, number the second one of these types of problems that we did. It looks exactly the same. We have an odd number of pairs of electrons moving around, which is great for thermal conditions. And so we can simply attach it and confidently know that we have the answer correct. So 1, 2, 3, 4, 5, 6. So there's 1. I believe that's 6. And then we're just going to add our double bonds where they belong. So there should be a double bond right here and right here. Does that look good? Yep. So this would be our final answer to, and I guess I could give these a name. These would be Claisen rearrangements. I don't know if I've already said that. These are Claisen rearrangements. Okay, so it might come off at first that this problem is actually just like the last four, but the big caveat to this problem is that you can't just jump straight to putting it in the pair position. So doing something that would be like a 3-5 rearrangement, that won't work. The reasoning is that you're doing this with thermal conditions as what's written above the arrow. And so why does that matter? So thermal conditions, we said that we like to have an odd number of pairs of electrons. And so if you move these electrons around, you'd soon realize that we aren't going to end up with an odd number, which is an issue. So we can kind of demonstrate that right now doing this. So that's the only way that we could suggest doing something like a 3-5 rearrangement. But it's, again, an even number of electrons, which is a big no-no here. So we want to get back to having an odd number of pairs of electrons. So instead of doing would be like a 3-5, let's do something that we know works, so a 3-3 rearrangement. So let me erase some arrows. And so let's say a 3-3 arrangement, we'll do that. And so our first intermediate gets you to this spot. And it's a propyl group, so just like this. So now, before you jump ahead, I wouldn't tautomerize first. I'm not sure if it brings up any issues, but it'd be a lot easier, and again, we still have heat, it'd be a lot easier if we just went on with putting this propyl group in the position that it needs to be in. So we can do that just fine if we, let me use my white color, if we move electrons down this way, doing something just like this. And that's perfectly fine. It's not like a Claisen. We don't have that oxygen to facilitate this rearrangement, but it's an odd number of pairs of electrons moving around in the final product, although I'm not going to draw that immediately after this arrow because it's going to be its pre-tautomerized form. But it will lead us into something that's aromatic. So what do I mean by that? Well, I mean that we will end up with this sort of thing going on here, just like this. And we'll get that. And so to get to the final answer, all we're going to do is just write tautomerization. Because again, that's just an enone. So enones will easily tautomerize into their enol if given the chance, and you also have created an aromatic ring. So that would be the mechanism for this particular problem. Okay, so for this last problem I have here, it's another one where you just figure out what the mechanism would be. And I guess I could give you guys what the final product would be. If you don't want to know what the final product would be, and you just want to try to figure it out on your own, go ahead and try to do that before I write it down, but I'm going to start writing it right now. So it would look like this sort of thing going on. And you could have gone to this without actually, the mechanism that you drawn could have gotten you to this product without even me telling you that it was going to end up this way, of course. Although it isn't indicated, you could assume that it's going to be some sort of exothermic reaction, and there will be a little bit of heat in your flask at some point. So I didn't write it originally, but it's kind of implied. But in case that was a part that stumps anybody, there's going to be a little bit of heat in here. Let's go ahead and try to figure this one out, and then we will talk about it. So the first thing that might be the most obvious thing is just go back to the first couple chapters of general chemistry or organic chemistry, excuse me. And let's just proton transfer. So electrons from our alcohol, we're going to see the strong acid and pluck off the proton, leaving us with essentially just water hanging out at the top of this six-member ring. So there's that water. So now you can, it's perfectly fine, and especially since we said that there was going to be a little bit of heat here, it's perfectly fine to suggest this group, this water molecule falling off on its own, so doing something like a SN1, or actually it'd be an E1. Just do heterolysis with it so that it falls off. That's okay because we have two double bonds on either side of it that will do some resonance to stabilize it, so that's perfectly fine. Leaving you with this. So now at this point, we have to figure out a way to get this butyl group up to the top of our ring. So best way you can do that is now to do a sigmatropic rearrangement. Looks kind of weird, but, and let me go over this arrow real quick in white just for consistency. But if we suggested doing something like this, and letting electrons come down, and then through that carbon and attacking this carbocation, we'd end up with this intermediate. And it's really close to our actual product. Looks like we have everything where it needs to be regiochemistry-wise. So now to get all the way up to the final product, really simply, and there should actually be a positive charge right here. To get up to this final product, recall from benzene chemistry that if you had something like chloride floating around and you had that carbocation, chloride is going to be a strong enough base to pull off this proton and reform that benzene ring. So let's go ahead and suggest that. So there's your Cl minus. Let it go, pull off that proton, reforming your benzene ring. Getting you all the way back to the product and the final answer.